Recording in progress.
Hi, in this video, we are going to apply the von Neumann stability analysis to number 2 of the 6-part series and show the requirement for stability that we discussed in the last part. Okay, so here we can see the equation that we found in a previous part of this series. I think it was part 1, and then the general solution using the von Neumann stability analysis. And it's the infinite sum of a time-dependent coefficient times the solution that we found in part 2, where you can see that the first piece is position dependent and the second piece is time dependent. So if we take this solution and apply it to our equation and then eventually implement it, we can apply the von Neumann stability analysis and we can see what our bound is for R. So the first thing that we want to do is we want to apply it to R. So it's TJN is equal to this because our spatial position is discretized into increments of delta X, and that is multiplied by this because our time is discretized into increments of delta T. So our TJN plus 1 would be TJN times e to the negative thermal diffusivity k squared delta T. So now we're just gonna plug that back into the equation. So we'll leave TJN plus 1 as it is, and then we'll factor out TJN and continue to simplify the equation. So if we pull out TJN, we have 1 for the first value minus 2 times R for the second value times e to the ik delta X minus 2 plus e to the ik delta X. Well, this is negative. Okay. Yeah. So everything in the parentheses is everything in the parentheses in our original equation. If we pull out TJN, and then obviously TJN would just be 1 if we pull out. So, okay, from here, we can simplify this using Euler's formula. So I'll go ahead and write that. And that is e to the ix is equal to cosine x plus I sine x. So using this, we can simplify this to, or we can simplify that inside part at least. So then it's going to be TJN still factored out, 1 plus 2R. Oh, this is a plus up here. Yeah. 1 plus 2R times cosine of k delta X minus 1. Okay, so we have to notice that if TJN, or the absolute value of TJN, is greater than 1, this equation will go to plus or minus infinity and cause that instability that happened in the coding of part 3. So we know that that is an issue with the R value. So if we set bounds to this expression that we have and do a little bit of math and simplification, we can figure out what those bounds actually are. So if we say that the absolute value of the 1 plus 2R times cosine, that part in the parentheses has to be greater than 1, we can go ahead and write that out. So 1 plus 2R cosine k delta X minus 1 has to be less than 1. And so that means that about the absolute value, it has to be between 1 and -1. So let me just write that in right here. Actually. Okay. And then if we subtract 1, we can do this. So it would be 2r cosine k x -1 less than 0. And then we can divide by 2. Okay, and the smallest possible value for the cosine k delta x is -1. So the smallest possible value for this whole expression in the parentheses is -2. So knowing that, we can set the bound for r. So I hope that's okay. Yeah, so we can just say that r times -2, which is our smallest value for in the parentheses, has to be greater than -1. And then we can just divide by -2. So 1/2, and then that flips our sign. So r has to be less than 1/2. And this shows the instabilities of the previous differencing scheme and the constraint r has on this function and the requirement for stability. So thank you for watching.